Hello there, Mr. Sutton here, bringing you the IM3 Honors Chapter 3 quiz review on complex numbers.
In order to simplify this radical, we have to deal with this negative inside the radical. To deal with that, we're going to split this radical up basically into the square root of -1 and positive 150. The square root of -1, that is what I is. So if I take the square root of -1, I can pull an I out of this radical and put it next to the -2 out here. So I can write -2i and then radical positive 150. And then I can go ahead and just simplify that radical like I normally would. So now 150, the biggest perfect square that goes into that, is going to be 25. 25 times 6. Square root of 25 is 5. 5 times -2i is -10i. And then we still have that radical 6 left over. In order to simplify powers of I, we need to figure out where in the sequence a certain exponent is landing us. Remember that there's really only 4 different answers you can get from I to some power. Either 1, I, -1, or -I. And that's all going to depend on whether you can reduce this exponent to a 0, 1, 2, or 3. To figure out which it is, we divide the exponent by 4 and find the remainder, and that tells us where we are in the sequence. So 73 divided by 4, remainder is going to be 1 because 4 goes into 72 equally, so there's 1 left over. So that means that I can rewrite I to the 73rd as whatever this remainder is, 1 in this case. And then we just have to know what I to certain powers, either 0, 1, 2, or 3 is. In this case, I to the 1 is just I. On this one, we're trying to simplify I to the 80th. So we're just going to have to figure out where this is in that cycle of 4. To figure that out, we divide the exponent, 80 in this case, by 4 and find the remainder. Since 4 goes evenly into 80, that's a remainder of 0, which means that I can rewrite I to the 80th as just I to the 0. And then I to the 0 we know equals 1. In order to add complex numbers, we need to meet a few conditions. It would help if these were not in parentheses anymore. And since they're each just being multiplied by an invisible positive 1, we can just drop the 2 parentheses there. But if we had a negative in front of this second parentheses, then we'd have to distribute the negative, so be careful with that. The other condition we have to meet is we should only have constants and I to the first power. I to any power 2 or higher can always be reduced either to a constant or just I to the first power, either positive or negative. Now in this case, we only have constants and i's to the first power, so we just have to combine like terms. 3 plus 5, that's going to give us 8, and we always write the real number first. And then 5i plus 7i, we add it just like we would add 5x and 7x. So this is going to be 12i. In order to add these imaginary numbers together, we're going to have to first reduce them to powers that are either 0, 1, 2, or 3, because we know what those powers are. So for each of these, we need to figure out where we are in that cycle of 4 by dividing each exponent by 4 and taking the remainder. So for 41, divide that by 4, and you've got a remainder of 1, because 4 goes evenly into 40. So we can rewrite this first term as 6i to the first power. This next term, well, let's see, 4 goes into 104 evenly. So the remainder on 106, if you divide that by 4, would be 2. So we can rewrite this as 4i squared. And then finally, 35, if you divide that by 4, you get a remainder of 3, because 4 goes into 32 evenly. So that means this is really 7i to the third power. Now once we've got these reduced to either 0, 1, 2, or 3 powers, we just turn them into either 1, 0, or 1, -1, I, or -I, depending on which power it is. I to the first power is just I, so this is just 6i for that first term. I to the second power, that's going to be -1, because you're basically multiplying the square root of -1 by itself. So this is 4 times -1, which gives us -4. And then finally, I to the third power, that's going to be -I, so I can rewrite this last term as -7i. And at this point, I can combine like terms. 6i minus 7i, that's going to be -I, and we still have that -4 hanging around. So just writing the real number first, I'll write -4 minus I. On this one, we're trying to multiply 2 complex numbers together. The key for these is to do basically what you would do if it were x instead of I, so normal multiplying rules, only if you get an I squared, you have to simplify it to negative 1. So let's go ahead and do this one. Distributing the negative 4i to each term, we have negative 4i times 8, which is negative 32i. Negative 4i times 5i, that's going to give us minus 20i squared. And the only thing left to do is this I squared is really negative 1. So instead of writing all this stuff here, I'm just going to write plus 20, because negative 20 times negative 1 would give me positive 20. So then my answer is going to be positive 20 minus 32i. And since these are not like terms, I cannot go any further. In order to multiply these complex numbers together, I basically need to FOIL them, just like if this were negative 1 plus 3x and negative 7 plus 8x. And then there's one little extra step at the end. But let's FOIL first. So we have negative 1 times negative 7, giving me positive 7. Negative 1 times 8i, that's going to be negative 8i. And then 3i times negative 7, the inners here, that's going to be negative 21i. And then finally 3i times 8i gives us plus 24i squared. So this 7 can stay the way it is for now. These i's here can be combined to give me negative 29i after that 7. And then this 24i squared, well, I squared, we remember, is really negative 1. So this is really negative 24 out there. And then 7 and negative 24 can actually be combined now. So this is going to be negative 17 minus 29i. For this problem, we're trying to multiply these radicals that have negatives inside. Now, the key with any radical that has a negative inside is, as your first step, you should immediately take that negative out as an I. So in this case here, we've got negative 4i radical 4 times 3i radical 10. And if you don't do this in the very beginning, you end up with the wrong answer at the end. You have the wrong sign for the answer. So just do it right away. So now we can just multiply the outside stuff together and then multiply the inside stuff together. And we're doing those multiplications separately. So negative 4i times 3i, that's going to give us negative 12i squared. And then 4 times 10 inside the radical, that's going to be radical 40. Now you could have turned this radical 4 into a 2 pretty much right away, but I didn't. I'm just kind of giving you the generic approach to any one of these problems, but you could have taken a little shortcut here if you wanted. All right, so at this point, we have an I squared, which is really negative 1, times a negative 12 is going to give us a positive 12 out there, and I still have to simplify this 40 a bit, so I'm going to split it up into the biggest perfect square, which is, well, 4 times 10. Square root of 4 is 2. 2 times 12 is 24. So then 24 radical 10 is our final simplified answer. On this problem, the reason that we have to simplify this is because we have an I in the denominator. It counts as having a radical in the denominator, which is off limits if you're trying to be all mathematically proper about it. So in order to fix that, we have to multiply the numerator and denominator by I. And now once we've done that, we're going to have negative 3i over 7i squared. And we just have to simplify this I squared. I squared is really negative 1. So that negative and this negative out in front basically cancel, and you end up with just 3i over positive 7. For this problem, to simplify it, we have to get that I out of the denominator. I'll do that by multiplying by I over I. So distributing in the numerator, we end up with 4i minus 8i squared. In the denominator, it's going to be negative I squared. And now I'm going to simplify those I squareds to negative 1s. So upstairs, we've got, let's see here, negative 8 times negative 1 is really positive 8. So that's 8 plus 4i. I'll just write the real number first. Might as well do it now. And then down here, we have negative 1, which is really positive 1. And of course, there's no reason to leave something with a divided by 1. That's just silly. So this is going to be 8 plus 4i fully simplified. On this problem, we're trying to simplify this quotient. And this one's a little different than others because we're dividing by a binomial. There's an I, but there's also another term down there with the I. So in situations like this, we can't just multiply by I over I, because then you'll end up with a 4i. This I will be squared, but this one won't, so that'll be an issue. To get rid of this I down here, we have to multiply by the conjugate of the denominator. So basically, multiply by the denominator, but switch the sign of I. So we're going to multiply by 4 plus I over 4 plus I. And this is completely legal because we're just multiplying by 1, just like simplifying fractions. So now in the numerator, we're going to do some distributing. 2I multiplied by 4, giving us 8I. And then 2I times I is going to be plus 2I squared. In the denominator, we've got basically a minus b times a plus b. So we can use our a squared minus b squared shortcut for this. 4 squared is 16. I squared is, well, just I squared, and we're going to subtract that. Now we're going to simplify the I squareds to negative 1s. So in the numerator, this 2I squared becomes a negative 2. And then we have a plus 8I up there as well. And then down here, we're basically adding 1 if we're subtracting negative 1. So that's 16 plus 1. And then just one more little step. 16 plus 1 is 17. And there's no way to reduce this any further.